أهلا بيكم في بودكاست كربون. معاكم أحمد رجب.
That's fun.
Yeah. Okay, hello again. Welcome everybody to a new episode of Carbon Podcast. And today we have a very interesting topic. And I think it's touching a lot of industries. And we are going to discuss a lot of interesting stuff. So I'm very happy today that we have Brandon with us. And we also have Muhammad, an old colleague. It's almost like 20 years. Of friendship, even more. So I'm really happy to have you guys here with us today in our episode, and I'm sure that we will add a lot in this episode. So welcome to Carbon Podcast.
Thank you.
Thank you.
Thank you. So let's start. Let's switch the gears. So as the episode today, we are going to talk about the research and development, specifically in the petrochemical and the fertilizer industry. So we need to shed some light on the what is the importance of the research and development, the R&D in this industry. Like, what's the bottom line for this one? Why we are doing the R&D? Because everybody is hearing that okay, we are doing R&D. Many corporates are doing, like, we have R&D department and we are doing some development. We have some new inventions. So we need to first give the background about the R&D and why we are doing the R&D. So let's buckle up. Let's go ahead. Yeah.
You want to take
Okay.
that, Mo?
I mean, you can start if you would like to.
No, I think your
It's
answer would be better than
open
mine.
discussion between friends. Yeah, let's go ahead. Yeah.
So,
Yeah.
in my opinion, like in our research and development in general, when it comes to engineering, it's about solving a problem. That's the whole purpose of our profession.
Right.
Which, bottom line, it means you are improving the efficiency of your process in one way or aspect. Like, either you are completely transforming the whole process by shifting to a different feedstock to get your end product, or finding alternative products that can give you the same application, in a very efficient way, or the how I can say this, the ground state kind of level of efficiency, which is like you have the same feedstock, you're going to the same product, and you're trying to be improving the energy conversion throughout your process itself. So this is just like my opinion about like what the bottom line of the research and development should be, because at the end of the day, any of those three alternatives is going to be having a business value one way or another. Every time you're improving in efficiency, it's going to have a business value. It will have an environmental value. You cannot get those two knobs without hitting that efficiency knob. You would be just tricking yourself, because otherwise, if you are targeting an environmental aspect and everything else the same, that means you're adding another treatment unit of some sort. So it will be penalizing your business in a sense. The other way around, if you somehow, if everything is lenient and there is no kind of regulations, well, I don't need to be adding anything regarding environmental impact. Like, it's going to vary by a country because these are environmental laws. And in that aspect, the environment will be penalized for the sake of business. So the only way you can actually like compromise both sides, actually like make both of them winners, is basically the process efficiency itself. So that's everything on my end.
So like a lot of that is bigger, better, faster, stronger, and here recently is cheaper. Right? There's so much competition on price. A great example is the first industry I started off on in was wood products, and I was making particle board. And 2 years after I left my facility, they actually shut it down because they established a new facility in Brazil that was bigger, better, faster, stronger, and cheaper, and we couldn't compete. We spent multiple six figures to upgrade the facility, the technology, and it wasn't even close. So they shut it down. And in my head, like, that's the big incentive for R&D, right? Nobody's spending the money for goodwill for no reason. They're looking for that return on their investment, right? Can I make this cheaper? Can I make more of it? Can I use less resources when I do it? Is there an environmental impact? Like a lot of European nations have that environmental incentive. So can I cut my emissions and get some additional profitability out of it?
Yep. Fully agree. Yeah. So, and my perspective as I was working again in the R&D, so it is like the translation of the market needs, whatever the market needs, as you mentioned, that reducing the resources or reducing the waste, producing a new product, a new grade for some certain application, or doing some energy optimization or whatever, to translate the business needs from the market and make it like doable in the plant scale.
Right.
So this transition, the in-between process, this is the where the R&D like jumping in and start to add some value here.
Absolutely.
Because many people think that the R&D it's only consuming money from the corporates, and we are only spending a huge amount of money for nothing. But the truth is that no, we are translating from the business to the real life production. So yeah, this is a very important point. Yeah. So we need to add more like what are the let's give our audience like more insights on the techniques and the tools, the skills, the headache. I would say, yeah, the real stress in the R&D, because some people thought that R&D it's only wearing the white lab coat and just running some experiments in there, and that's it. So it's really a huge work behind this in the backstage. So we need to shed some light on this one as well. Yeah. So let's go ahead.
Absolutely. So, I mean, Brandon would be like stressing, can put his vote after this, because we got the chance to be working a lot in research and development on so many aspects before. Engineering wise, you are going to really need, I mean, this is basically what's happening in the background, in your core that nobody actually sees. Everybody sees pretty much like the tip of the iceberg, your results, your outcome. And your core is going to be built from engineering perspective on how much you are super knowledgeable about like the core physics, mathematics, and chemistry. This is just like beyond like we don't need to be like we don't need to go into like the mass transfer or heat transfer. Basically, we can lump sum all these aspects of science into chemistry, physics, and mathematics, and basically you understand every one of them and what the core role and when I'm using which one at which stage. So once you basically get that foundation, and that's gonna be like taking a lot of time. Of course, like in your undergrad, and then probably like in type of years, 5, maybe 8 years, for example. It depends on how fast you are going to progress through the industries in general. You build all this experience, you connect your theoretical background with these applications, then you start to be like coming up with concepts, theoretical concepts, just like because you're tying everything. And then once that comes into perspective, you already know the theoretical foundations. That's mathematically speaking how it looks like. Then you start be like, creating some type of design of experiments in order to go to the next phase, which is the lab scale, for example. And from the lab scale, given the design of experiments that you have, now statistical work is going to be complementing your physics background. And based on that, you try to basically look, okay, was my core assumption in physics, was it okay? Or was that assumption not okay? I need to be actually including that parameter in the first place. And then you keep repeating. And if everything is compatible between the lab and the theoretical work, then the next move is going to be the pilot scale, which is going to be almost 100x. I mean, in a sense, you're talking about like going from grams to pounds.
Complete. Yep,
So it's
you
not.
got it.
So it's not a huge in that aspect, but it will be sufficient because now you're going from the pure ideal environment where you are controlling everything by the
Got it.
ppm, in a sense, temperatures and everything like that. And if you are having heaters or heat exchangers and stuff, everything there is like basically, you're controlling the flow temperature. There is no utility anymore. For example, you're not dealing with impurities in your feedstock that you're experimenting with. How much variable the pressure, like the process controls and everything like that. You go to the pilot. Once you go to the pilot, now you're trying to polish everything, and you see how the significance of everything that you haven't been testing in the lab on the pilot scale. And once you take everything in there into perspective and matches everything that you're expecting it, how it works, then pretty much you're almost 95% done in terms of like the process R&D itself. And most likely you are already got the mechanical work as well, because you're going to be working with a mechanical engineer when you are at the pilot level. And once that takes the lead, you already connected all your core. You have all the statistical analysis to be complementing that, not the other way around. And pretty much like you can actually go to the commercial scale. And at this point, there is a very high confidence your process or your idea is going to flourish.
So two really good examples of that would be like the new nylon process design, and then the high temperature nylon that we scaled up at Ascend, right? So like as an example, I was running the pilot plant at the time that Mohammed and I started working together, and we were working on developing this high grade of nylon. So it was a copolymer nylon 6.6 and 6T. And eventually we developed this process for it to make it, which is strictly controlled off of like pressures and temperatures, and it would create this curvature, like this process path. But none of us actually knew what the process path was, if that makes sense, right? We knew if we followed this process path, we made the product every single time, but no one actually knew what it meant physically.
Right.
And so one of the things that kind of came out with me and Mohammed working together, right? And he kind of said it, always going back to your fundamentals. One of the things that we had to experience at that facility was fundamentals were just kind of useless. They were thrown out the door. They had no value. And so once you establish this process always works. There's really no reason to ever question it again. When we started to question it for like this new nylon that we're manufacturing, that process path that we developed turned out to be the solid liquid equilibrium curve, which is important because there's, there's now a physical interpretation to what this process path is and what it means. And then him and I working together, we extended that to nylon 6.6. Nylon 6.6 also has a solid liquid curve. But whereas with this high temperature nylon that we're manufacturing, where we don't have any history of making it, we don't have any baggage, nylon 6.6 we've been making for decades, not just us, companies throughout the world. And when you start to look at this new process path, which we call the new nylon process design, right? What you see is we are so far off of where we could be because the company, and it's everybody, right, got in the habit of making this material and they said it's good enough. They never stopped to question, why is it like this? And so for years they missed that opportunity. I don't remember what the final figures were, it was so long ago, but off the top of my head, I'm thinking you cut out like 80% of your thermal demand out of the actual reaction, and you cut your time by 25 to 50%, depending on the grade and combinations, things like that. And that's just for the materials we looked at. And all that was sitting down and asking why. And as Mohammed said, doing some lab studies where you actually are intentional with what you're doing. You know what parameters you want to measure, and you're taking your time, you're being careful, and you're analyzing the results. Then taking it to a pilot, doing the same thing, being careful, being methodical, and trying to understand, does this fit physically with what you think theoretically should be taking place? And then when you're successful, do it on the commercial scale. Do you see the same thing? Does it actually work? Did you miss anything? I know back when I worked at a specialty chemical manufacturer, there was this one material that we made where they had basically made in the lab. They said it's the easiest process ever. Don't even sweat it. And I asked if we could run in the pilot scale. Just that's what we're there for, just to see. And they're like, no, it's so easy. Don't sweat it. They just immediately scaled it up. There was this one impurity that they made at the lab scale. They said, if this impurity shows up when you scale it up, you will not be able to separate it. The product will be useless. That impurity showed up when they scaled it up. They made a bunch of material they couldn't sell because they decided not to pilot it because they thought it was too easy. What was the point? And then there you go. So now you have this process that doesn't work because you just decided to skip a step and skip ahead.
And just like to stress what like Brandon said earlier, it's basically because the core itself requires a lot of work. Like it really takes a lot of toll on you, like, as a person who is qualified to be running these things. You invest in yourself, you invest a lot of time to understand all that. You probably, of course, you invest a lot of money in order to get what you need to get in terms of like developing yourself. And that is going to get translated into a result for the business, for the environment, for everybody.
Yeah.
The problem is it always treated as an underdog. Like it's always somehow like you should be like somehow it's taken for granted. Like if you have this degree, you're supposed to be doing this by heart. And then the problem is I want it to be super fast. So pretty much you have so many entanglements of so many things that are unrealistic. And then pretty much like you get a realistic output, which is
I was gonna
basically
say, to that point, how long did it take you to get funding for your lab scale experiment to prove that you're right?
for which part? For which one? I mean, like
For the new
depends.
process design and send, not the other stuff. They send work.
Oh, geez. I mean, I think like for the lab, for example, for the renovation, like just to get everything to work, I think that was like 2 years or so, just for the lab. Now you're talking about like probably another year and a half, and probably Brandon knows that.
Very
To just
typical.
like
It was 1 year to scale it up.
Yeah,
So,
very typical.
and the reason I bring that up, as I'm assuming we want to talk about like real life, one of the challenges is it's as much as we within our industry understand the value of R&D, that's not always well understood by those above us, right? So took what 2 years to get the lab equipment to actually run the experiment, because if you don't have the equipment, there's no point in running the experiment. And then 30 seconds run the experiment and get your data point and say you were right. And then it took maybe 3 months to do it on the pilot scale, just whatever. But then that was done, and for a fact it works.
As I remember, we have done like almost like even on the lab scale, you have been visiting the lab when you got the chance first time to be like we got to meet and working together on that. We almost like did like 90 to 110 experiments on the lab. Like it wasn't like a matter of like finding the point that matches what I think and just like go with it. It was like literally like so many grades. And there was a special grade that actually like Brandon was really interested in terms of cleaning the claves as well, that basically justified why before it was a problem to be using this type of material. And then later on we found out like we were pushing that limit in terms of like severe conditions, and it really did not need to be in that severe conditions. But this is like basically the chicken or the egg. Like it's funny how like everybody wants to be unique as a company in general, if it's a company XYZ. But when you look at company X and company Y and company Z, for example, the problem becomes like everyone wants to be unique with some differential product or some differential process efficiency, but yet when it's actually handed to them, somehow like, oh well, why nobody else did it? It was like, I mean, how are you gonna fit those two? Like when you look logically, it's like somehow you're dealing with a wave function of an electron. It's like I want to be like differentially better than someone, and at the same time, well, I have this potential process. Like, why nobody else did it? Like, well, you're gonna have to be like,
you have to invest the resources behind it.
You have to vet it. I mean, I'm not like saying
right.
We're not saying you should not vet it, but like you really should be vetting everything based on physics or based on your core, whatever fundamentals that you're working with. And then especially if it matches everything and it goes through the normal standard engineering scale up and it matches everything else, then you should be convinced as as a business in general that yes, you are sitting on something that's unique. You had some type of skill that like other companies did not have. It's just simple. But like once you start to be like going into like philosophical questions of like why others are not doing it and why you're not gonna get anywhere, because like you somehow want to be improving yourself and be better than someone else, and somehow you want to be better than someone else and yet have their process, and somehow when it's applied into your business it works better for some reason. It's just like a weird cycle. But like this is the low level like kind of improvement that everybody can actually harness in general. And that, like we mentioned, like yesterday, I am 100% like at this point in my career, 100% guaranteed sure that the process technologies overall, whether it's chemical industry or any other industry right now, it looks like it did not move an inch from
Yeah.
the 70s.
I will second that. Having worked in a few places,
We
absolutely,
are all on
100%.
the same page. Yeah.
Yeah, I'll
And
second that.
and what I'm stressing here, I'm stressing the process aspect of the industry itself. There has been developments mechanically. There have some developments in terms of anything beyond the chemical engineering or process engineering. But like if you look at the fact where the chemical engineering came to be a chemical engineering discipline,
Yeah.
I really think we did not even go beyond the first layer, like improve it at all.
Fully agree. Before moving to that, before moving to that whole part, just to conclude the last thing. So again, the R&D, it's mainly like as you all mentioned, it starts with the paper first. I call it the paperwork first. So we start reading, we start doing some the basic principle calculations like thermodynamics or even moving some computer software simulation, something like this. And then we decide on that one, because this is the hardest part, because anybody working in the R&D, he should think like in a two-way, like back forward and feed forward, like from now and what will be happen next and what should I get at the end, and think like in the back verse way. So before going to the lab scale or the bench scale pilot plant or whatever, you should first have a very clear, like a very clear idea what I'm going really to do. And I think the most common thing that many R&Ds are it's not right thing that, but many R&Ds they are going with this mistake that they are going into the experiment or the R&D with a solid perspective. So he really needs to reach that point of like results. So he starts to squeeze everything, all the parameters, just to reach that point and just to prove his like perspective or whatever. While he's missing a lot of the chances if he going there with very open mind. Okay, I define what I really need to like examine. Like, okay, I define my parameters. What are the dependent and independent parameters? What I really need to look forward, but don't miss the opportunity for yourself that you need to examine and you need to test many things. Maybe you find something that it wasn't on your plan, right? So you may come up with a very good idea or a very good correlation or whatever, and then you can find a even better idea that you came with in the first place. And doing the as Brandon mentioned that, okay, so before going to the scale up, that we need to make sure that everything I did on the bench scale or the lab scale, it should be consistent with whatever I'm going to do in the pilot plant, and it should be also consistent with whatever I'm going to scale up to the pilot or sorry to the plant scale.
You got it.
Yeah, so I have seen again many things that, okay, we are doing that on the pilot plant, and with the existing facilities that we have, nobody need to change anything. But we know that we will miss something because it's not consistent. There is many like differences between the pilot plant and when we are going to scale it up to the plant scale. Yeah, so this is very important idea, and I have seen many projects come to fail because they missed this point. They thought that, okay, it's working in the pilot plant, it should work on the plant when we scale it up. Yeah, so this is it create a big mess, I think. Yeah. So let's move to the hot topic because we are all on the same page on that one, because many people thinking with all the I'll not mention any names. I can name and shame, but I'll not mention any names. Many of the companies who own the technologies and the chemical engineering on the chemical industries, petrochemical refineries, fertilizer, whatever, they are selling the idea that we are improving, we are providing a new type of catalyst, which is really adding a lot. We are really doing a great job in R&D. We are really adding a lot to the science and the chemical engineering. While in the truth, or the black truth, this is not the case. We are still living in the 60s of the chemical engineering. This is what I'm thought. Maybe earlier, maybe later, but this is what I'm thinking. Yeah.
Right.
So let's move to this hot topic. Yeah, we need to illustrate this to the audience.
So there are two things that we need to just clarify in that area. Like, first of all, the problem, the reason why I mentioned earlier that we need to be having a strong, that's the whole point of like a person going to engineering school, for example, or going to physics or any other STEM school.
Yeah.
The whole point there is that you are going to be working in a discipline that at its core is represented by something called nonlinear algebra, not linear algebra.
Yeah.
And basically that is the core differentiator between a person that's working as an abstract mathematician versus engineer or physicist, etc. The problem is, if you look at everything that has been developed mathematically wise in an abstract fashion, everything there has been developed based on something called linear modeling.
Right.
Basically, because everything is some type of represented in a linear fashion in a vector, some kind of vector space, X, Y, Z, etc. So pretty much the simplest example would be like having a vapor pressure of a pure compound versus temperature. Linear model pretty much is going to be like, linear algebra, for example, despite how simple this is. Someone is going to basically have like some type of polynomial representing the pressure as function of temperature. There is two problems there. The first problem is going to be you cannot extrapolate that because we know there is a critical point and there is no vapor pressure beyond the critical point. The second aspect, you'll never know the elementary part. You never know the elementary function, and knowing the elementary function is the most important things because, like, you have Maxwell relations, and your second and your first derivatives is that the stage where everything is somehow related. It's not the function. It's not the y itself that's related. You have the dy by dx and d2y by dx2. So this is the core differentiator between physics and truly abstract mathematics. The second aspect to this, if you look at everything we have in technology-wise, software, statistics, or machine learning, all these aspects, which is pretty much derivatives of derivatives of derivatives, all stem from based on linear algebra. So you have a problem there. The first problem you're going to have is like you better be knowing what variables are impacting your problem. So number one, you're going to have to know what variables are going to be impacting. So if you don't know them, that's going to be like, from the start, you don't have any core solution. The second problem is the foundation of linear algebra. So you are going to get stuck because pretty much everything that you are trying to target domain-wise, you're going to really need to zoom in on all your functions to be represented by the linear, basically the tangent problem. So this is the main issue, mathematically speaking, of everything that we have technologically wise. Now, moving to the other aspect, whether it's catalysis or whether it's some type of like chemistry related issue, the problem is when you look at the technology development across any kind of technology, whether it's polymerization or fertilizers or any other aspects in petrochemicals, you're going to find there has been a trend, true, that every time I improve the catalyst by some way, like, moving to improve the kinetics in the reactor by having, some type of like a more active catalyst, etc. There has been a trend, there has been association between what you're doing and somehow the energy improvement of the overall process. Then as you keep doing that, so basically, the principle of minimum return, you keep developing the catalyst, you keep improving the catalyst, and by the time you find that there is no more correlation, you keep improving,
Right.
and your process is plateauing, like it's not moving
Right.
anywhere.
Right.
And for some reason, people keep insisting to keep pushing that variable, despite we're not going anywhere. And that's the other aspect. And actually, we should be blaming the chemical engineering in general on that, because we haven't been doing our core to be showing how our discipline is very how can I say it, is very built to be actually solving these problems. And we somehow throw out the fact that we need to let the scientists, in terms of polymer scientists or chemists or physicists, for example, to, okay, you guys can take it from here. We're just going to be the executionary arm for you. Just tell us what we should be doing. So this is basically, in a nutshell, I'm trying to summarize it, how the problem looks like in the chemical engineering, technically speaking.
I'm going to take a different perspective, right? So I've worked in 4 different industries over the last 10 years. And I think we all agree that technology really hasn't moved since the 60s, wherever you want to put that timestamp. And Mohammed and I had talked about this at length, right? So the 2 examples I think of are ammonia and polymerization, just because those are the 2 most glaring examples, right? So polykondensation reactions, specifically like 9166, all of that kind of came out of World War II and that whole scenario where there was a critical need, and if you failed to meet the need, like there is a literal civilization impact for your failure. Ammonia synthesis, right? Same idea. World War II, if you fail to deliver, the literal civilization is going to be impacted by your failure. You know what I'm saying? There's not a your business is going to go under and that's it.
Yep.
Like literal people will suffer because of it, right? And so coming out of World War II, it's been this long period of peace and tranquility, which is great. But then you also see innovation slide. I mentioned 4 different industries, and every single one of them is completely stagnant from a technological standpoint. I work in stainless steel manufacturing right now. That process has never changed. The only thing, like what Mohammed said, the only thing they've changed is the mechanical, some of the electrical. The process itself has never been touched outside of furnaces, just because of some boiler requirements. So you can just kind of, piggyback off of that technology. That's it. And you're talking about these huge installations. I think stainless steel accounts for something like, or maybe all steels, I can't remember, but it's like 2% of all carbon dioxide emissions globally.
It's
Something like that. It's a staggering figure, and that process has never changed. Nothing about it's changed. And I always go back to what we were talking about when we started looking at polykondensation reactions. The one question we always kept asking was why? Why does your process look like this? Why are we seeing some of the things we're seeing? And if you never ask the question, like you can't improve. You won't improve.
Yeah, I mean, like pretty much like
hard,
what Brandon, yeah, like what Brandon is like basically saying there is like, you just confirm it. The development originally, unfortunately, the core development was always
not to pause you. The ammonia synthesis example. If you, I know you haven't published your PhD, but like that's a good example you could talk on. Literally.
Yeah. I mean, like in general, like Brandon mentioned about ammonia, for example, the drive was survival. You literally had to put people in survival mode in order to really improve, which is sad, because like seriously, you need a world war in order, you need a global conflict in order to be getting pushed around.
I agree.
But that is just like tells you like the magnitude that we as humans, we can actually improve our processes or our technologies if we have the motive. And it's sad, it's kind of sad that your motivation has to be like, I'm gonna die if I don't. So it's and like, if you
I agree.
We mentioned yesterday was like Fritz Haber, for example, and you have like when he was developing this in 1915, like World War One. We're not even like World War II, so we're talking World War One.
Yeah.
And the whole thing was developed because of literally the human survivals.
Right.
The human population was exponentially growing, and unfortunately, the rate at how the growth of that population is not keeping up with how much we have naturally, like abundant fertilizers.
Absolutely.
So technically, you need there isn't going to be enough fertilization in order to be having enough crops to feed all these people.
Right.
So that's literally where this technology was developed, and it's literally survival. You're not going to be eating. Forget about having a gas for your car or something.
Mm.
And once it was developed, it was super unique. It was really a huge deal because if you look at the trend of the human population after that, it was insanely significant. It's like
Right.
less than 1 billion, and now we are 6 billion. That's in a matter of almost 80 years or so. So that was if you compare it, was I don't know, 200,000 years of the human. It depends on how you define when the start was. Um, that's a significant thing. The problem is, as Brandon already knows, that if you would look at the Fritz Haber setup in the lab,
Yeah.
you take a snapshot of that, and you go to the most advanced
You got
ammonia plant, and you look
You've
at the
got
back
it.
end, and you look at the ammonia
Same.
sensors. It's a copy paste. I mean,
It's
yes,
same.
of course you had a better turbines, you had better mechanical, you had a better mechanical input. You had, of course, catalysis development that has been taking place. Um, that has been correlating, like I mentioned earlier.
Yeah.
Catalysis and mechanical efficiencies has been correlating with improving the process efficiency or energy consumption itself. But once you hit the 90s, you pretty much hit a plateau. So and you
Right.
keep and unfortunately our reaction was pretty much doing the same thing or improving the same variable that you're already telling you hey, there is nothing much there to improve. Yes, you might have a good thing like a catalyst or something like that, but this is not your why. Your why is improving the process energy efficiency.
So
Right.
to that point, how
Yeah.
significant, and I know we can't discuss it fully, how significant is the patent you're about to file on the ammonia synthesis process? Because that is a perfect example of
Uh,
how important R&D is and
uh-huh.
how long we went without asking very basic fundamental questions.
It's definitely going to be super significant, for
You know what I'm saying?
very,
But that's
very
what it
step,
was. It was just
almost.
right.
It's definitely a step change in that direction. But the point is, we keep losing the track of our why.
Agreed.
What's our function?
Agreed.
Our function is improving the process efficiency, energy
Right.
utilization. But somehow we get lost into the sparkly kind of thing, shiny things. Hey, I'm going to be having a new catalyst.
Yeah.
Okay, well, I want to relate what you're doing to that why. And somehow, your
Right.
attention gets so confused because you were just a minute ago, you want to talk about energy consumption and you want to be more green or more efficient. Suddenly, we are talking about some new catalyst because it's made out of, some new chemistry or, some type of noble
Mm.
metals or something like that. But it's all R&D whatsoever it's always necessary. But the most important aspect is going to be which X in our
You got it.
development, whether it's
Right.
X1 or X2 or X3, is going to be impacting our Y significantly. This is going to be this is going to be the core in all these R&Ds. And of course
Right.
that this is the most significant part. But you can measure, you can literally, how can I say that, you can literally scale that example into every aspect of chemical industry. And I'm not
Agreed.
going to be shying away from saying probably semiconductor industry, for example, and other aspects that pretty much I really think we are at the point in a human development that the approach of I'm gonna somehow find some miraculous element or
Mm.
compound or something that will solve my problem is over. We are at the
Yeah.
point that we really need to understand what's happening behind the scenes
Yeah.
in order
Right.
to end up engineering that with everything that's abundant. I mean, if you for example, if you be saying, hey, I will be able to make all these type of processings for computer industry, for example, if I have these amount of lithiums. Okay, well, we're not living on an asteroid. Unless we are actually going to an asteroid, fine, we can do that. But again, it's again, egg or the chicken. We need to go to the asteroid, but we need again noble elements in order to travel there. So the problem becomes, it's not like, hey, I found that. And basically that's what Fritz Haber, for example, did in the beginning. Fritz Haber, when he started all his work as a scientist, he worked with osmium, he worked with uranium, and he found out, like, pretty much in order to scale up with BSF, he found out that there isn't enough osmium in the whole planet to run the first small scale plant. So you have to come up with another method of actually making it. So yes, there is the core part where, like, you found a way, a method,
right,
to create a product. Then you're gonna need to engineer your system with the abundant resources that you have logically to create your product. You cannot be like saying, well, if I have like Einsteinium, I can be creating all fancy products in the world. But like then you come in the paper and basically say, well, there isn't enough Einsteinium, so that's your problem, guys. I already, I did my part.
absolutely.
So this is literally what we are at this stage. Like,
Right.
There should be some realistic. There should be some realistic behind this, and also consider all the limitations that we have. Because I have read like hundreds of papers. They are very optimistic, but we don't have the resources yet.
Well, the nice thing about it, like, if you once it's vetted and it's actually real thing, if that resource or that metal or that like material that was able to create this type of functionality, the next question is going to be why that functionality was created in the first place.
You've got it. That's the big question. That's
going to be the big question. And once like you already have that answered, you can actually like now go to your toolbox and basically say, hey, I am living on planet Earth. I'm not living on an asteroid. Here's the resources that's abundant to me, and here's the combinations that I can be using in order to be creating that, or basically reproducing that functionality again.
Yeah, I think the motive or the motiva behind this, as you mentioned, we have been discussing this yesterday as well. Like for example, from my like experience in the polymer industry, like for the synthetic rubber, it didn't move an inch until the World War II, while the world has become like has a huge shortage of the natural rubber. So they thought that, how can we like produce a synthetic rubber? So suddenly out of nowhere, there was a huge leap in that industry, and many technologies has came out to the scene with many companies. I think that it started in the US and then in Europe, and right now until the 80s again, or maybe the 60s. Let's be more fair, and it's stuck there. I have never seen any further improvement since that time. Like in 60s, most of the papers or most of the patents, most of the abstracts or theses, even in nowadays, it's still built on whatever has been done before. And one funny thing that you mentioned also, that it is not linear. One of the funny thing that I have been read through the polystyrene, and I think Mohammed, back in 2017, you were trying to reach out to me to discuss something about the polystyrene. All the patents, all the theses, everything about the polystyrene, and if you read there, they will start their introduction by, we are neglecting the gel effect. So all the studies, all the experiments, they neglect totally the gel effect or the gel impact. So how can I really decide those results are accurate, and you have been like neglecting a very crucial parameters there. Yeah. The other thing that I have been into, that we were studying some heat transfer and some reactor design, a polymer industry as well. And we were only depending on the very basic thermodynamics and heat transfer equations. And I have to keep asking that during the polymer formation, the volume is changing, molecular weight is changing, and also the properties are changing with time that we are developing the polymer inside. It keep reacting, the chain is like growing, and
Yes.
many parameters are changing. But
Yes.
we neglect that because we don't have that like capabilities or whatever to track every femtosecond the changes on the polymer formation, and then we can calculate correctly or accurately, precisely the change in the heat transfer, so we can design the reactor in a very precise way. So this is very important point. I have a book here. Maybe it is. I think it's reflected. It called 0 to 1, but it was mainly talking about the business and the IT business. But I think it is the same on chemical engineering as we have been talking about.
Yeah, well,
We are-
if you like really look at the polymer industry in terms of like being in terms of chemical industry itself, as chemical engineering is trying to be getting there, the polymer industry is probably the most unfairly treated from chemical engineering perspective, because if you look at the polymer classes that we get and stuff like that, like there's no chemical engineering anywhere.
No,
Like literally, it's a whole statistical thing. Somehow
you got it.
you have some monomer going to dimer, trimer, whatever, and the whole equation is somehow represented by rate equation. That's just one single rate of consumption of monomer, and that rate of consumption of monomer is vanishing into polymer. What that polymer is, nobody knows.
Exactly.
It has some repeating unit, just for simplicity. And of course, it's not like that. The only member that is forming there, you're gonna have gel formation, basically. It's like in nylons, for example, you're gonna have like a lot of side products that you don't want them there. Whether it's like cross-linking or something like that, you don't want any of this to be there. The other problem is nobody actually goes back to the upstream process. Everybody is already taking for granted that you already
got it.
you have an end product. It's called PS or PSXX or PSX or whatever. And hey, now I need to do the improvement. I was like, this kind of pretty late, buddy. I mean, like you're super late in that. Whatever you're doing now, it's like almost like having a treatment unit.
Yes.
That's assuming you already know what you're looking for. So that is the aspect in general, and you nailed it in general. Again, if you go to the polystyrene and synthetic rubber, again, it was super critical, as the nylon 6 was super critical, because both of them were critical products for the warfare. One for the parachutes and one other one for everything that has a vehicle in it. So you understand now, unfortunately, I don't want to be like, I don't want to be sounding pessimistic, but somehow real innovation only happens when you have like almost like a global struggle.
Right.
You can't every time, like, which is it's weird. It's like every time people prosper economically, the more we lose that for some reason.
Well,
Like,
and I was going to say this, right? One of the big things that has changed, and I don't know how it is with your universities overseas, but our educators that are leading the next generation, their one focus is actually not to educate, at least in the States. Their focus is actually to publish papers. Their focus is not to publish quality papers. Their focus is to publish papers. They can literally just put down their name. As long as they publish it and somebody will accept it, they are meeting their goal. And it's wild how much that's changed, right? And so instead of having, and I think back, because we've had some conversations on some of the best and brightest minds of our generations, the amount of time that they spent working on one topic to really vet it and understand it for it to be considered complete. And they spent their whole life, and that's all they had to show for it. But it was so substantial to our humanity and to the knowledge that we have today. And fast forward, and now we need 10 papers a month, and it has to be significant, but we're really not going to vet it because there's 100 other guys doing the exact same thing. And so you end up kind of diluting the pool of significant work. And you end up de-incentivizing bright minds from really pursuing something of significance because you've now put a time constraint and a quantity constraint. I have less time to do it, and I have to put more out in the same amount of time. So everything that's being published and pursued is less and less significant than what it used to be. And there's no real incentive, right? Like there used to be an incentive, human survival. That's a pretty good incentive. What's the incentive today? And again,
it became the KPI. It became the KPI, the quantity, not the quality.
Right. Right. Because
I mean, simply like if you look at like for example, like the space industry.
Yeah.
Like we have only been super powerful in that dimension only when there was a Cold War.
You got
When
it.
there was no more Cold War, I mean, like there's no point. And
You got it.
the sad problem about that now is like we have all the blueprints of what happened back then and these people literally had almost 0.1% of the technology.
It's wild. Yes.
They literally, like if you look at, like, for example, Apollo missions, for example, their computer was like almost like the same level of a calculator nowadays. So just like go figure how like with this type of technology they were able to do it. So obviously
Went to
it's
the moon
not
with a flip phone. Like
yeah.
that's the analogy I've all heard. That's crazy.
So it's definitely it's telling you like like kind of like prosperity is not associated with like how many apps you have on your iPhone. It's literally about the people themselves. The other problem is like we have significant documentations from that era, and we are literally copying and pasting, and we are really bad at copying and pasting. We're not even developing new things. We are literally bad about that. Like we are literally having the blueprints with all the new technologies that's available to us, and we cannot basically successfully. There has been some significant improvements in terms of like getting back the rockets and stuff like that, like to be in order to be like recycle them in order to not keep every time you need the new
But
rocket
again,
and stuff.
the incentive, right? That's financial.
But yeah, exactly. And then is financial. But at the end of the day, we really did not move anywhere beyond the same low orbit. I mean, like seriously, we can't even go to the moon again. I mean, think about it. We have no really collection whatsoever, and on top of that, we have a lot of space junk, as we call it, around the planet. That at some point we're gonna start like seeing a lot of of that breaking down and falling and stuff like that. But just like we really have to be super serious about like what we call a technology, because having a, for example, if we are going to be defining technology as being somehow convenient, well, sure. I mean, you can pretty much like claim any food app, like a delivery app, for example, that's a technology achievement. But what exactly did it improve? But like, if you look at the other aspect, somehow, like what we are living nowadays, in terms of like chip industries, and everybody is like fighting in order to be having the most advanced chip, and we're forgetting the core of like what makes them work. Everybody's fighting in that direction because like at the end of the day they are trying to basically be superior, but the problem, you have limited resources. So we are again going back to the same aspect of like the unique kind of like elements on the periodic table that's not abundant on the planet. And instead of like actually going into answering the question behind why it's working, we're just like going for the easy peasy kind of thing. Just let's look for lithium, let's look for gold, let's look for osmium. But like we already answered that before. We already have said like these are pretty rare metals, so you need to be revisiting the functionality. So
Like a good
that's
example, when we look at like the polycondensation work we did, all the improvements were at the end. But the biggest improvement came if we looked at the beginning, which everyone just said it couldn't be changed. The work that you're doing with ammonia, all the work's been done at the end. But your patent is based on just looking at the beginning, and it completely changed the entirety of what follows. so much of what we do is, and again, I don't know how much of it is cultural or our drivers, right? We typically pick the thing at the very end that we feel comfortable, that we feel like we can accomplish and we can succeed at. But then our impact is so minuscule.
Mm-hmm.
We ignore everything that led up to that point. When in reality, it's how much could be improved if we just simply started from the beginning and said, what was the original goal we intended to do? I've been in some places where they'd actually drifted from what they intended to do. So, like a good example I'm thinking off the top of my head is I have a process we use to make stainless steel it's called neutral electrolytic pickling. It's called neutral electrolytic because it typically operates in neutral pH, except it doesn't. Most modern neutral electrolytic pickling processes actually operate at a low pH, around 2 to 3, somewhere in that range, because you get better conductivity, lower resistance. It's just better. When I took over the role at my facility, their pH was around a 5, a 6, right? And they were actually intentionally dosing caustic to the process to control the pH. So I just asked the question, why? Because I don't really understand why we're doing that. I have papers that show you shouldn't do that. They're like, well, we want to protect the electrodes from dissolving. Okay, so we protect the electrodes from dissolving, but now we have a process that doesn't work. And then out of the blue, we had a, we'll call it a mishap, but never let mishap go to waste. I got us to take out the caustic. We never put it back. We've cut out 40% of our electricity consumption by taking that caustic out. And it all goes back to asking the question, why? Why did we have it there in the first place? What did we try to solve? I haven't had any electrodes dissolved. I cut out 40% of my electricity consumption. My process is running better. My quality is better. And all it was just asking the question, why? Why did we do that? And if we can't answer that, we should probably take a deeper look.
It's a twofold, because like asking that question, number one,
Right.
is like the question is almost like asking the right question is almost halfway.
100%. I agree.
Literally, you're almost halfway of
agree.
getting to the idea. The second aspect is like it's going to require, unfortunately, if you need to be making a big impact, you are going to really need to be addressing something that nobody else has questioned. It's that simple. You cannot basically go into like a big pile of patents that has been having a specific approach to the problem, and somehow you take the same approach, and somehow, like, nature is not going to be biased to you. Like, it's just everybody else is doing the same thing. Like, why I should be giving you?
Most of my R&D that I've seen is taking the patent and just applying it in our process. That is R&D at a lot of facilities.
Yeah, that's a core problem, because, like, I mean, sometimes you can find a loophole or something significant that nobody else have seen, but whenever you see that loophole, there's gonna be like a pile of work that you're gonna need to really do before you get to that big significant jump that you are looking for. It's not gonna be like, hey, I found that hole there, and it somehow is gonna jump the solution in front of you. So yeah, I mean, like,
one of the things you always say is, why do we ask the problem to fall to our level of competency? Why don't we rise to the level of the complexity of the problem we're trying to solve?
it's exactly
there's so much.
Yeah.
Right. There's so much of that in industry where we're like, the problem's too hard. Linearization, as an example. Everything we do is linear because linear is really easy.
Yeah.
But then we end up with a bunch of solutions that don't really always apply, and sometimes they just don't apply at all. And again, it's us trying to simplify something that's complicated rather than rising to the complexity of the problem we're trying to solve. A complex problem isn't going to be solved by a simple solution. It just isn't, right? Like, you look at the work of Einstein. Einstein's solution is beautifully simple now that he went through the complexity of how to get. But you know what I'm saying? Like,
yeah, it really took a lot of effort to be actually simplifying the whole idea, and it's literally that,
But the whole is so complicated.
It's like almost like, there is an uphill battle,
right,
in order to get to that idea, and once the idea is there, you are going to find out like how simple the solution is.
Right.
But the problem is you're going to have to go through that uphill battle. You cannot just like expect that you copy and paste or basically mirror someone else's work and somehow it's going to be super significant. You are asking, I want to be unique. I want to be like significantly impactful. that means you are going to be really need to address the problem in the same aspect.
You got
Like
it.
have to be like something drastic in order to be doing that. You cannot be now you're gonna be now that's a wishful thinking now. If you are basically I want to be impactful by repeating someone else's work, well, why the other person did not gain that? In order to be impactful, you're gonna have to be super unique, which means that
Yes.
the idea that you came up with, nobody else approached that way.
Yes.
And I think this is not practical nowadays. Look at all the other like technologies. They are only depending on copy and paste, right? And then innovate. Not the other way around. Like innovate
Yes.
first, and the innovation has been. I would say we can save a lot of resources from the looking for the uniqueness and the innovation. And
Mhm.
just Ahmed mentioned many times that we should look at the abandoned resources and the abandoned work that has been done before and build on that. I think we are missing a lot of opportunities out there. The other thing that I just need to highlight this one. Maybe this is like the solution for this dilemma, that it should be starting from the university time, right? Because as we are all know and agree on that, it became like we need to publish like hundreds of patents,
You
100
got it. Right.
papers, and I'm sorry to say that it's all trivial.
Mhm.
It's not introducing anything new. It is very trivial. I
Mhm.
have read many papers, and they said that we are using some data science and that like fancy terminology. And when you really look at the paper, it is the very basic statistics, very basic, like nothing.
Yes.
Mhm.
It is like looking for the uniqueness, as Muhammad mentioned. It became like the making everybody's hallucinating about that. Okay, I need to be like more unique. I have to find something more innovative.
Mhm.
While we are missing a lot of opportunities on the other hand, that
Mhm.
we really need to look at it.
There are super, like if you look at three categories, there is a super severe mismatch between schools, established
Yeah,
industries, and startup industries. So if you look
yeah,
at startup industries, like taking for example, space industry, or looking at fusion, hydrogen fusion, these industries that literally want, if they can find the talent, they need the talent. But the problem is that here is the mismatch where it comes. The schools are not satisfying that because like everything molded as we have already spoken about. The established industry is like going in a spin. They don't know where they want to improve, but they don't know how to, there is no specific real strategy about how to improve. And now when you talk about the startup industries like space or semiconductors or hydrogen fusion, anything that's super on the edge, pretty much. They need the skill set.
Right.
But here's the problem: the other two parts, the school and the established industry, already eliminated or basically reduced that substantially.
yeah,
Because as you know, you're gonna really need to have a lot of endurance in order to maintain your competence, because like with everything that we are going through, at some point someone is going to be like saying, I'm just going to maintain the status quo, I'm going to just do what I need
A
to be
lot
doing.
easier. Right.
It's a
That's a
lot
lot
easier,
easier. Yeah.
super easier. So pretty much like the ground itself is not, you know is not capable of giving you that output that you need for those startup industries. So startup industries are going to be the most significant in terms of looking for talent because they need to. Their whole investment is built on that. If they can't make that technology work, they go bankrupt.
yeah.
Right.
It's the survival that we were talking about. If you
Mhm.
have an established industry, well, it will be nice to be having extra bucks, but do I really
That's
need them?
100% accurate. Yes.
That's pretty much what it is. And then, of course, like schools in general, like you mentioned, when the metric or the KPI is X papers, which is I'm not technically against that, but like if you have X papers without any other constraints, that's a problem. I mean, it's super problem. And it's not only my personal opinion. There has been a lot of communities in physics and in chemistry. You can like really look them up, like on YouTube, for example. They have been talking about the same problem. They have been literally like saying we have an exponential rise in paper production, and we have almost nothing matching that technology-wise. That's a big problem. I mean, like, like they were just like stressing what Brandon mentioned earlier. Back in time, we didn't have as much papers, but there was a huge leaps in technology. And I'm talking about beyond engineering. I'm talking about like physics and everything.
Right.
But now we have, you would somehow associate that, hey, we have this insane amount of like flood of papers. We must be having something significant coming up. But no, you have exponential jump in paper production, and there is nothing being translated in any applications. So that's actually like a some type of red flag in a sense that, hey, we need to come as a community. We have to be actually revisiting what we actually trying to maximize here.
Yeah.
Yep.
Fully agree. I think we already covered most of the points that we need to discuss this episode, and it is really interesting. And if we have the chance, we could have spent like days talking about this. I know that. Yeah.
Absolutely.
But, I'm really grateful for your input, Muhammad and Brandon. It has been very fruitful discussion for the moment, and I think it's already we already exceeded 1 hour now. So
That's crazy.
yeah. And I'm sure that it will add a lot to the audience, and this is the main target for this podcast. That we need to add a value to the audience, make them like more getting more ideas and getting more like the truth behind the industry. And now we like touch base on the very crucial thing, which is the research and development, which is the main and the core driver for all the industry, the chemical and petrochemical industries for sure. And I hope that one day that we like wake up one day and find that we have a good advancement and a good lead in the technology of petrochemical. So again, I really thank you for this fruitful discussion, Muhammad and Brandon. And I'm sure that we will have another episode. We need to cover a lot again. So I'm really thankful for this episode here. Thank you.
Absolutely. Thank you so much. I appreciate that.
Thank you, Brandon. Yeah, thank you for
you guys.
Thank you.
Yeah.
Okay.
Everyone. Bye bye.
See you. See you.